I will start the fourth lecture of week 4 of this course. In this lecture, I will try to give an idea of why we are interested in symmetries. We looked at all the point symmetries, we looked at the translational symmetries, and now we want to ask the question why symmetries are interesting and why did we do this whole exercise in the first place. Okay. So week 4, lecture 4 will be topic of symmetry and symmetry notations. So I will also show in this notations, I will show how these symmetry notations are usually depicted in the planar notation. So now we have seen the various symmetry operations, the symmetry elements. So if you have a point, you can have an inversion. If you have a plane, you can have a reflection. You can also have a glide reflection. Whereas if you have a line, it can be a rotation axis, it can be an axis for rotoinversions, or it can be an axis for a screw rotation. So these are the different symmetry elements, and these are the various operations that are possible for each of the symmetry elements. Now notice that all these symmetry elements, all the symmetry elements that are listed have to be consistent with translational symmetry of the crystal. So all symmetries have to be consistent with lattice translation, and by lattice translation I mean translation by one unit of the lattice, one or more units of the lattice. So all these symmetry elements have to be consistent with the lattice translation, and this actually ensured that there are only few types of rotations and few types of reflections and so on. Okay, few types of screw rotations, few types of rotoinversions. So basically this ensured that you have only 2, 3, 4 and 6 fold rotations. Okay, and similarly you just have I mean 2 bar is actually identical to inversion to I. So you just have rotoinversions of 3 bar, 4 bar, 5 bar, okay, or 6 bar. Similarly, we saw that only certain allowed screw rotations were present. Also, one of the effects of this statement that all symmetries have to be consistent with lattice translation is that there were only very specific translations associated with the glides and the screws. So glides and screws only had, so the glides and screws had only specific translations. What I mean by this is that if when we were considering the glide reflections, we always looked at either translation by half of the unit cell or quarter of the unit cell. Okay. Now you can ask why did we not consider other glides, okay, by different amounts, and it turns out that you don't need to consider them because an arbitrary translation by an arbitrary distance would not be consistent with the lattice translation. So there are only certain kinds of translations that will be consistent with the overall lattice translation. Okay. Now so the question is, why do we need symmetry? Okay, and I'll give a few reasons why we need symmetry. Okay, let's start with the following statement that we used. So we had defined a crystal as a lattice plus a basis. So if what we mean by this is that if you want to generate the entire crystal, okay, what you do is you take the basis atoms, okay, and you put them at each of the lattice points. You take the basis and put it at each of the lattice points, and that will generate the crystal. Okay. Now, the basis may contain many atoms, okay, and often it contains atoms of the same type. For example, the diamond cubic structure, okay, can be thought of as an FCC lattice with a 2 atom basis, okay. And if you have something like the unit cell of silicon, okay, then every atom is silicon. So, the 2 atoms in the that form the basis are identical, okay. So, now what this suggests is that you could change this picture of crystal as lattice plus basis could be equivalently written in the following form. You could write it as a combination of lattice plus symmetry plus asymmetric unit, or I'll write specifically asymmetric unit. Okay, so this corresponds to, this is like a smaller version of the basis. Okay, so you take the asymmetric part of the cell, you apply the symmetries, okay, and then you do the lattice translations, and you should get the entire crystal. So, in other words, this symmetry plus this asymmetric unit is what is generating the basis. And what this allows us to do, this allows us to give to it greatly simplifies the notation for the crystal. So allows us to describe crystal, description of crystal in very short notation. So, essentially we will see this, that we can describe the crystal using a very short and brief notation. Okay. You do need to describe what this asymmetric unit is, okay, and we will see a specific example of this in the case of the, we have already seen that if you take, we have seen it in the case of the diamond cubic. Okay. So, now later on we will see that this lattice and symmetry, they combine to form something called a space group. Okay. So, they are described by a terminology called the space group. So, we can really think of the crystal as a space group plus an asymmetric unit. So, this will be done in the following week. Okay. So, it is equal to space group So, really one advantage of symmetry is that you have a very nice notation for these space groups, and you have a notation for this, and you have to actually say what the asymmetric unit is. So, if you specify this asymmetric unit, that is the smallest repeating unit, okay, then you can really specify the crystal structure. So, you need the asymmetric unit and the space group. Okay. So, for example, we thought of this diamond lattice as so for example, we saw the diamond cubic as FCC plus 2 atom basis. Okay. And what we will see is that this is a space group. Okay, I won't and the space group, I will just write the name. Okay, we will discuss this names a little later. So, FD3M, this is the space group of diamond plus 1 atom. Okay, so if you just if you just say the one atom basis with this space group, okay, you will generate entirely, you will generate the diamond cubic structure of something like a silicon crystal. Okay. We will discuss this later. So, this is the name of the space group nomenclature. So, this is space group. So, this will be discussed in week 5. Okay, so this nomenclature will be discussed in detail in week 5. So, but essentially the idea is that you can describe it as this one atom basis, which is the smallest symmetric unit of the silicon plus the space group, and you can do this for all sorts of groups, not just for silicon. So, for all crystals this can be done. Okay. There is another motivation for using symmetry, and let me write it here. Okay. And again we will just say that we will discuss this later. So, symmetry affects, I will just put it in a block here. So, this will be done again in some later week. So, symmetry affects X-ray diffraction pattern intensities. Okay, and we will see this later on when we are talking about X-ray diffraction. Okay, so this will also be discussed later, but these are the reasons why we are interested in symmetry and why we spent such a long time discussing the symmetries. Next, you can ask the question why there are only specific choices of translations. Okay. So, this is so for example, for glide planes we took only half or 1/4. Okay. So, 1/4 was in the case of the diamond glide, but all other glides were characterized by half unit translations. So, the question is why only such fractions are allowed. Okay. And we already said this, okay, but it is worth re-emphasizing this. Okay. It's so these are the only glides. Okay, these have to be consistent with overall lattice translation. That means if you translate by 1 unit, along any of the axis A, B or C, okay, should give you an identical structure. Okay, should give you a completely identical structure. So, whatever glide planes you have should be such that if you they should be consistent with this overall lattice translation. So, for example, if you say a glide plane of half, if you look at the half glide plane, okay, so you do a glide reflection of 1/2, okay, and if you do this 2 times, okay, so if you do a glide reflection of 1/2, okay, and let me take along A for example, okay, so 2 successive glides will generate lattice translation by A. Okay, so remember that glide reflection corresponds to reflection in a mirror and a translation along along some direction. In this case we took the example of an A direction. So now, and its translation by half unit. So when you do two successive glides, okay, so then then you will end up reflecting again. So the second time you do it, you will again reflect. So you will come back to the original sense with respect to the plane of reflection, and then you translate by A, you will get shifted by A. So the effect of two successive glides is just a lattice translation by A. In other words, the two mirror reflections will cancel each other, and what you will be left with is just by a translation by half A followed by another translation by half A. So that is an overall translation by A. Okay. So clearly this glide reflection is consistent with the symmetry of this overall lattice translation, and similarly you can show even for the diamond glides. Okay, we can show that they are consistent with the overall lattice translations. Okay, and you can similarly show that there will be other glides that are not consistent with this overall lattice translation. Okay, so if you take arbitrary, if you translate by some arbitrary distance, okay, then it could be that it's not consistent with the overall lattice translation. Okay, so these are some of the reasons. I mean, these are not very very easy to see, okay, to exactly work out, but at least you can see why you only use specific choices for these translations. Now let us look at the notations for different symmetry elements, okay, and these are notations that are usually shown on the planar diagrams. So on the planar diagrams you use these notations for symmetry representations, and it turns out that using these notations, okay, we can actually generate using these symmetry elements, okay, and an asymmetric unit, you can generate the entire crystal. Okay. So I'm going to talk about the different notations for the rotations, rotoinversions, and screw axis. So each of these correspond to some axis. So you could have an axis, and that could be either an axis of pure rotation or a rotoinversion or a screw axis. Okay. So let's look at this notation. Now let's say you have a order 2 axis, a twofold axis. Okay. So if you have a twofold axis, now it could be a it could be a pure rotation like a 2 axis. Okay. Then the notation that is used is now you could have a two rotation either in page, in the screen, in screen, that is in the screen, or perpendicular to screen. Okay. Now if it is in the screen, okay, a twofold axis of rotation that is in the screen is shown by this arrow, a line with an arrow. Okay. So that represents a twofold axis of rotation that is in the page. A twofold axis that is perpendicular to the page is shown. Okay, let me use a different. Okay, so that is perpendicular to the screen. Okay, is shown by an oval that is filled. Okay, so an oval that is filled is used to show that there is a twofold axis that is perpendicular to the screen. Now there can be other twofold axis. Okay, you can have a 2 bar, which is a twofold rotation plus an inversion. Okay, and this is shown. It is very similar to I'll show a 2 bar that is perpendicular to the screen. Okay, so if you have a 2 bar that is a twofold axis plus an inversion, okay, then you show it using this symbol. So it's like this oval, but there is a small hole inside to show that there is an inversion. Now there are other two-fold axes that you could have. So for example, you could have a screw axis. So if you have a 2 sub 1, now so this corresponds to rotation by 180 degrees and translation by half the unit cell. Okay, and this we will show it by. So if it is in the screen of paper, we will show it by this harpoon. Okay, so it's half an arrow. Okay, so a line with half an arrow. Line indicates that the rotation is in the screen, so it's along this line, and the harpoon indicates that it's a screw rotation. If it is perpendicular to the screen, then you show a regular two-fold axis, but you show it with this. Okay, and if you have a 2 bar sub 1, okay, if you have a 2 bar sub 1, okay, then you show it. You show it like a 2 bar with this screw. Okay, so this is a 2 bar sub 1. Okay, and we generally don't show the 2 bar axis in the screen of the paper, in the screen. Okay, what else you can have for the screw axis? You could have, I mean, these are all the possibilities that you can have for a two-fold axis. Now let's go to a three-fold axis, and I'll use a different color. Okay, so if you have a three-fold axis, okay, now there are many more possibilities. Okay, in this case, if you have just a regular three-fold axis, you could have a regular three-fold axis. Okay, and usually you don't show any three-fold axis that is in the screen. Okay, only two-fold axis in screen is shown. Okay, so let me emphasize this point. So usually only two-fold axis in screen are depicted. So in the screen only two-fold axis is depicted. The three-fold axis perpendicular to the page, all the axes are depicted. So if you have a 3, okay, perpendicular to the screen, then you show it by a triangle, a filled triangle. If you have a 3 bar, okay, then you show it by a triangle with a circular hole. Okay. If you have a 3 sub 1, okay, then you show it by a filled triangle with these extensions here. If you have a 3 sub 2, okay, 3 sub 2 is like rotation by minus 60 degrees and translation by 1/3, or you can say rotation by 60 degrees and translation by 2/3, and this will show it. Okay, so it's just that the lines are in the opposite sense. What else can you have? You could have so these are all the possibilities that you could have here. Now I'll just briefly show the other axis. Okay, I won't show all the possibilities. So for 4-fold axis, it is shown by a triangle. That's a 4-fold. A 4 bar will be shown by a triangle with a circular hole. Okay, and in this case, the 4 bar is actually shown in this direction, like a diamond. Okay, and again, all these axes are perpendicular to the screen. Okay, and I'll just show 4 sub 1. So, a 4 sub 1 would look like this. Well, okay, actually 4 sub 1 is again shown like a square that is split, and 4 sub 1 is shown this way. Okay. Now, you could also have a 4 sub 2. Okay, you could have a 4 sub 2, and I'll show it. So, the 4 sub 2 is shown by now only 2 lines are drawn. So, this is 4 sub 2. So, 4 sub 1, 4 sub 2, and if you want to show 4 sub 3, you show it again we use the fact that it is like a 4 sub 1, but the lines are drawn in the opposite direction, in the perpendicular directions. Okay. And similarly, if you have a 4 sub 3 with an inversion, okay, then there will be an empty circle in the middle. Okay. Now, I will just briefly mention the other two. So, if you have a 5, if you have a 6-fold axis, so I'll just mention very briefly how you show a 6-fold axis. So, 6-fold axis is shown by a hexagon, a filled hexagon. Okay, and you can use very similar depictions for all the remaining axes. So, all the remaining 6-fold axis will be shown in a very similar manner, okay, and so on. Okay, similarly, you have more of these 4-fold axis. Okay, I just wanted to show some of these. Okay, you might see them. You might see structures that are depicted this way. Okay, I'm not showing all of them. Okay, just showing a few of them so that you get a general idea of how rotation axes are represented in the planar figures. Okay, what about mirrors? So, mirror is a plane of reflection. Okay, and if it is a pure reflection, okay, and let's say that if it is perpendicular to the plane of the paper, it is in the plane of this. If it is perpendicular to the plane of the screen, or in the screen in the plane of the screen. So, those are the two possibilities. Okay. So, I'll say perpendicular to screen. In other cases, parallel to screen. Now, if it is a pure reflection that is perpendicular to the screen, okay, then it is shown by a solid line. Okay, a solid line is the symbol for a mirror that is perpendicular to the screen. If it is parallel to the screen, okay, then usually you draw lines along the crystallographic axis, so this indicates a reflection that is parallel to the screen. Now, in case your cell is not it's a tetragonal cell, okay, or then you will have something like this. Okay, in case the angle is not 90 degrees, okay, the angle between A and B is not 90 degrees, then you will show it in this way. Okay. Then what else can you have? You can have a center of inversion. Well, you can have a center of inversion, and that is unique. So, center of inversion. Okay, and that is just denoted by a circle, empty circle. Then finally, you could have glide planes, and you could have a variety of glide planes. Okay. Now, I am not going to, so these are glide planes are mirrors. Okay. So and there are a variety of notations for glide planes, okay, depending on what kind of glide plane it is, and what is the direction of the glide, where is the plane located. So, in the first case, when the plane is perpendicular to the screen, okay, then there are a few different notations. So you could have, now there are various symbols. So you could have a dashed line, okay, and this indicates that the glide is that the translation is half along line. Okay. So the translation direction is along this line, okay, along this line that is shown. The mirror is perpendicular to the screen, translation is along this line. Okay. Now, you could also have a translation of half. You could also have a glide plane that is perpendicular to the screen, but the direction of the glide is half, but normal to the plane, normal to screen. Okay. In this case, you use a dotted symbol. So the direction of translation in the first case was along this line. In this case, it is normal to the screen. Okay. Then, if you have a double glide plane, okay, so we talked about the E glide, okay, double glide. Okay, I won't discuss this in detail, but you can have something like this. So this represents a double glide plane that is perpendicular to the screen. You could have a N glide. Okay. Now, the N glide is again if it is perpendicular to screen, it is a line with a dot. So it is a dashed dot line is an N, that is a diagonal glide. Okay. Then you could have a diamond glide, that is D, that is a diamond glide plane, and this looks actually, I mean the symbol is very similar to the diagonal glide, okay, but there is an arrow that is drawn. Okay, there is an arrow to indicate that it is a diamond glide plane. So these are the various glide planes that you could have that are perpendicular to the screen, when they are perpendicular to the screen. Now, when they are parallel to the screen, okay, we saw that the pure reflection is shown by this little angle. Okay. Similarly, all the glides, when the glide plane is parallel to the screen, okay, then usually, since so you could have several different glide planes. For example, you could have a glide plane, okay, and if the direction of translation is along this axis, okay, it could be A or C, okay, or you could have a glide plane where the direction is along some other axis that is shown. Okay. So the arrow shows the direction of the translation. Okay. This could be A, B, or C. Then you could have a double glide plane, which would look like this. An E glide would have two arrows. Okay, that is an E when it is parallel to the screen. Okay. You could have a diagonal glide that would look like along some diagonal glide. So that is an N glide. And you could have a diamond glide, okay, which there are different notations. You could have something like this. This is a diamond glide. Okay, I'm not going to go into this in too much detail. Okay, because we won't be using it too much during this course. You could have things like this, where the arrow shows the direction of the translation. Okay. And usually this arrow, since the length of this arrow will be denoted. So, if you have a 1/8 translation or a 3/8 translation in this case. Okay. So, that these will be the length of the arrows. Okay. Now, again this would be a diagonal, this would be a diamond glide. Okay. When you show it in the plane, okay, this is what it will look like. Okay. So, these are the general ways in which all the symmetry elements are represented in various planar representation. Now, now we will talk about the planar representation of diamond symmetries. Okay. And here I want to show what the various screw axes look like. So, now if you recall the planar representation of diamond, okay, it looked like this. So, you had the atoms at z equal to 0. This was the z equal to 0 layer. Then you had at z equal to 1/4, you had these two atoms at z equal to 1/4. Then you had at z equal to half, you had atoms at the edge centers. And at z equal to 3/4, you had points that were located here along this other body diagonal. Okay. So, these are at 4 different values of z, and this was the representation of the diamond structure. Now, let us look at the symmetries. Now, you should keep in mind that we had there is an inversion center right between these two. Okay. So, it's along there is an inversion center at z equal to 1/8. Okay, at 1/8. So, this inversion center is at z equal to 1/8, and it is on the line that is bisecting these two points, by bisecting this blue point and this red point. Okay. Now, it takes a little bit more effort to see the other symmetries. Okay. Now, I'll show a location of a 4-fold screw axis. Okay. Let me use this color. So, there is a 4-fold screw axis, okay, that is located right here. Okay. So, this is a 4-fold screw axis that is located on right at this point. You can verify this if you rotate by 90 degrees, then this red point will go directly below the green point, and then you translate it up by you translate it by 1/4. Okay, then you'll get this point. So this is a 4-1 screw axis. Screw axis. Okay, that is located there, and now you can show that there would be another screw axis symmetrically located at this point. But this would be a 4-3 screw axis. Okay, in the sense, if you rotate it clockwise, okay, then this red point will be on top of the blue point, and then you have to translate it down by 1/4. Okay, alternatively, you can translate it by 3/4. Okay, so this is a 4-3 screw axis. Okay, and similarly, you can easily show that there will be a screw axis located here. That will be a 4-1 screw axis, and there would be a 4-3 screw axis here. So you can easily infer the presence of these screw axes, and now additionally there is of course the diamond glide plane. Okay, so the diamond glide plane, okay, which is shown in the following way. Okay, so the diamond glide. This is a diamond. This is a representation of the diamond glide. It is 3 by 8 and 1 by 8. Okay, so you can easily show that that there is a glide plane. So this that is parallel to the screen. Okay, and it is a diamond glide plane. Okay. Now, I mean you can also show symmetry elements on the other parts of the diamond. You can, I mean, just as this same symmetry element would also be here. Okay. Similarly, this symmetry element will be here. And so on. You can just complete the whole. Okay, so now you can also see that that the asymmetric unit of diamond. So the asymmetric unit of diamond is just this. This is the asymmetric unit. Okay. So this small 1/8 corner is the asymmetric unit. Okay, and you can essentially, whatever is there here is seen in all the others. So for example, you would have an inversion center between this red point and this blue point. Okay, this will be located at 3/8, or sorry, this will also be located at 1/8. Okay, you would also have inversion centers here at 1/8. And here at 1/8, and there will be other inversion centers, okay, between other connecting points that will be located at different distances. For example, here you would have an inversion center located at, so at no, not here. It will actually be located between this is at 3/4. So yes, okay. So there will be an inversion center right here at 7/8. Okay. Similarly, there will be an inversion center here at 7/8. Okay. There will be inversion centers located here and here. And similarly, there will be inversion centers located here and here. Okay. These will be at a distance of 3/8, and these will be located at distance of 5/8. Okay. And I am not showing in the other parts of this unit cell. Okay. Essentially, what I am trying to say is that you just need to know the symmetries of this symmetric unit, or what are the where are the symmetry elements, and essentially you are done. Okay. Now there are several other axes. Okay. For example, now this this is a four-fold roto inversion axis. So there are four-fold roto inversion axis, okay, located right here. So this atom has a four-fold roto inversion axis that is shown by, so four-fold roto inversion axis is shown this way. Similarly, there will be a four-fold roto inversion axis at this point, and at this point. Okay. So these are, and similarly you can show that it will be at all these other points, but I am not showing them. Okay, I am not bothering to show the remaining points. In fact, you can show that there will also be a four-fold roto inversion axis right here. Okay. So so there are several for each of these points, each of the points in the diamond cubic lattice, okay, acts as a four-fold roto inversion axis. So four bar. Okay. So there are also screw axes. Okay, I am not showing them here. Okay, but there are also other screw axes in diamond. Okay, which we had already seen earlier. We had seen some of the screw axes in diamond. I won't show them in this figure because already we have shown lot of symmetries already in this. So with this, I will conclude this fourth lecture of week 4 of this course. In the next lecture, we will summarize what we learnt in week 4 and then do some practice problems. Thank you.